So I will be talking about some work that was recently published in the Journal of Physical Oceanography. And I started this work when I was a postdoc with Fram Strait at Scripps Institution of Oceanography. And we were trying to answer this question: how much Arctic freshwater participates in the subpolar overturning circulation? So the rest of my collaborators are listed on this slide. And I have this nice satellite image of the east coast of Greenland in the background, where you can see sea ice that's being swept along the coast here in some coastal currents. And I like to show this image because it gives you more of a visual intuition for the area that I'll be talking about. So let's start by considering the surface circulation in the subpolar North Atlantic. In the red-orange arrows, I'm showing warm, salty Atlantic waters that flow northward and cool as they flow around the subpolar North Atlantic and the Nordic seas. And then in the blue arrows, you can see the cold freshwaters that are made up of Arctic river runoff, Greenland land ice melt, and sea ice melt, as well as, sort of over a broader scale, precipitation over this region. Now, each of these sources are expected to increase as climate change continues and have a broad range of impacts. The first of these impacts is on the local circulation. So here I'm showing, again, a satellite image where you can see a chlorophyll bloom that occurs right at the edge of cold, fresh Arctic waters and warm, salty Atlantic waters. So these fresh waters have an impact on primary production and biogeochemical cycling on kind of a local scale. Now, if this fresh water spreads into the interior, it can have an impact on dense water formation through convection, as well as carbon storage. So here I'm showing a column inventory of anthropogenic CO2 from Katiwala et al. And you can see that the subpolar North Atlantic really lights up as a hotspot for the storage of CO2. And this is thought to be through deep convection in this region. Another really interesting recent study showed that there's this link between fresh water that's spread over the large scale subpolar North Atlantic and the atmosphere. So in this plot, I'm showing in red freshwater events, and then in blue is the winter NAO, or North Atlantic Oscillation. And you get a general sense from this figure that the freshwater events are followed by an increase in winter NAO. And winter NAO is associated with a cold and stormy subpolar region. Now, in this paper, they go through mechanisms for how this works, but this is a really fascinating sort of air-sea interaction impact of freshwater spreading over a large scale. And then finally, many of you have likely seen these high-impact papers that claim that there's a link between the spreading of freshwater over a large region, so over deep convection, deep water formation areas, and the strength of the Atlantic meridional overturning circulation. So I hope that I've convinced you, or at least given you a bit of a flavor for the fact that freshwater has these significant impacts on climate. And this is especially true if it's stirred over a broad region. At the same time, we really lack a baseline of subpolar freshwater pathways from observations. So, as I introduced, I'm going to try to answer this question: how much Arctic freshwater participates in the subpolar overturning circulation from observations specifically? So now I'm zooming in here to the eastern subpolar North Atlantic. And the cutout at the bottom of this schematic is the OSNAP East section. OSNAP is a large observational program that includes many moorings, gliders, and Argo floats to try and characterize the strength and variability of the overturning circulation of the subpolar North Atlantic. I'll be focusing just on the eastern half of the OSNAP array because A, for simplicity, and B, because it's been shown in Lozier et al. 2019 that the magnitude and variability is really set in this eastern half. So you don't necessarily need to include the Labrador Sea to get a good general idea of what is going on. So in the schematic again, I'm showing in red and orange colors warm, salty Atlantic waters that flow northward through the subpolar Nordic seas into the Arctic, and also recirculate here in the eastern subpolar. In the light blue, I'm showing deep waters. And by deep water, I mean anything that's in the lower limb of the overturning circulation. So that includes intermediate Labrador seawaters, it includes overflow waters, anything that's sort of in the bottom half of the overturning circulation, I'm calling deep water. And then in these purple green arrows, I'm showing polar waters. These are, again, the cold, fresh waters that flow along the coast of Greenland. So we do know a few things. We know that the deep waters are fresher than the Atlantic source waters. So we know that the Atlantic source waters mix with some fresh waters, whether it be polar water or some of the freshwater sources I listed before, to create these fresher deep waters. We also know that the polar waters flow all along the coast of Greenland. So we know that the Atlantic waters aren't mixing with all of the polar waters to make the deep waters. Okay, and I made an attempt to try and sort of gauge how these fresh waters, how they compare with each other a couple of years ago. And in this figure, I'm showing in blue, kind of counterintuitively, I'm showing sea ice concentration just from 1 month where there was a particularly high sea ice concentration. And you can get a sense for how it flows here along the east coast of Greenland. And in the numbers, I'm listing estimates from the literature of sort of long-term average freshwater transports. So in black is land ice melt from Greenland, from these two different sectors. In red, I'm showing liquid freshwater transports from these different arrays. And then in green, here is a sea ice transport. And you can start to build a general kind of picture from this of, perhaps a lot of this freshwater flux is actually lost into the interior, doesn't flow right along the coast. Maybe you get a sense that the Greenland contribution is about a fifth of the total, say, of these liquid freshwater transports. But there's kind of a fundamental issue with making a figure like this in the first place, which is the issue of reference salinities. So, when we calculate freshwater transports from oceanic, in the ocean, we have to choose a reference salinity. So here's the equation we use to get those freshwater transports. And, in that study, I chose 34.9, just because that's kind of the division between Atlantic waters and polar waters. And you can get a general sense that maybe Atlantic water has to mix with this amount of freshwater in order to get that amount of freshwater transport. But freshwater sources with zero salinity, it doesn't matter which reference salinity you use, they will always be constant. It's just the volume transport of a freshwater, of the freshwater in that case. So if you want to compare an oceanic freshwater transport with a zero salinity transport, such as the Southeast Greenland melt, it really matters which reference salinity you choose in comparing them. So what we really need is a framework that doesn't rely on a reference salinity and acknowledges the full circulation, especially if we want to get a sense for how much participates in the overturning circulation in particular. So here's that framework, an observation-based volume, salt, and heat budget. So as I said before, in this schematic, the southern boundary is OSNAP East. And at OSNAP, there are observations from 2014 to 2018. The northern boundary for my budget is the Fram Strait here in the north, and then the Barents Sea opening. And then I'm going to be using heat fluxes and surface freshwater fluxes from the JR55 reanalysis, and as well as its implementation in NORASM. And more specifically here at the northern boundary, you see that there are many references listed here. This is a compilation of many different observations taken by many different folks. Specifically, what I'll be using is a product put together by Tsubuchi et al. 2019, which goes from 2004 to 2010 and includes monthly averages. So you might have noticed here that these observations all span a different period of time. So OSNAP is 2014 to 18, the northern boundary 2004 to 2010, and then the heat fluxes and freshwater fluxes, we have those span a larger time period. I did do some sensitivity analyses to try and understand if it mattered that I'm using observations from different time periods in trying to get this mean picture. And the basic result from that was that as long as the observations are long enough, so at least a couple years, that's really more important than having the observations at the same exact period of time, as long as you're within this kind of decadal range here. So I'm not showing that today. I'm happy to talk more about that, but I did check and am confident that it's a reasonable thing to do, to put these observations all together and try to get a general mean, steady state, present day picture of how freshwater moves through this system. So in order to really understand how freshwater is moving through the different components of the circulation, I've split up the circulation into water masses that reflect the transformations that I'm interested in. So at the southern boundary, we have Atlantic water that's coming through from the south, and I'll call that AWS. So Atlantic water comes in from the south. In the northern boundary, we have polar water that's coming in from the north. That's polar water north. And then through the surface, we have surface freshwater fluxes and heat fluxes, which are this Q. So those are the three inputs. And then the three outputs reflect the three different limbs of the circulation, or three different transformations that I'll be focusing on. So the first is this overturning transformation. So the transformation of into deep water south, DWS, which is the overturning transformation. The second is this estuarine transformation, which is a transformation into polar water south, so this cold, fresh output in the south of the domain. And then finally, there is some Atlantic water north that flows through the domain into the Arctic. This is not really a focus of the current study, and it ends up being a place where I can kind of put a lot of the things that I'm not interested in, but it's necessary to complete the circulation to include that flow into the Arctic. Okay. And what I'm going to do is I'm going to place these all into a budget framework that is a weighted linear inverse model. So I'm going to use the observations as initial conditions and then close the budget, and specifically close the conservation of volume, conservation of salt, and conservation of heat. And the unknowns in this budget are all of the water mass transports, as well as the surface freshwater transport and the heat flux. So that's three equations, these three conservation equations, and 7 unknowns, the 5 water masses and the 2 surface fluxes. I'll be treating the surface freshwater flux as a water mass that has 0 salinity, 0 temperature. And again, the initial conditions and the salinities and temperatures of the different water masses, I'll be getting those from observations. And I forgot to say this at the beginning, but if at any point, I'm happy for folks to interrupt and ask any clarifying questions along the way. Okay, so here's a geographic breakdown of the water masses as I define them. So each of these panels shows the mean velocity at OSNAP East here at the southern boundary, and then Fram Strait and Barents Sea opening, which are at the northern boundary. At OSNAP East, I'm showing in this thick black line the isopycnal of maximum overturning. So that's the line that separates the upper limb of the overturning circulation here from the lower limb of the overturning circulation. I'm defining everything that's below the isopycnal of maximum overturning as deep water south. And then this small vertical black line here separates the cold fresh waters, which is the polar water south, here on the shelf and slope of Greenland. And everything to the east of that is the Atlantic water south. So to get the properties and transports of these water masses, I integrate over this entire region to get some representative salinity, temperature, and volume transport for each of these. At the northern boundary, again in black, I'm repeating the isopycnal of maximum overturning from OSNAP east, just to give you a sense for the fact that it's a lot denser up here in the north. And then in red is the 0 degree isotherm, which actually coincides very well with this isopycnal of maximum overturning. Everything that's lighter than this 0 degree isotherm is defined as polar water north. So that's the inflowing cold, fresh waters to the system. And then everything else is Atlantic water north. So this again is kind of a crude way to lump everything that is not the focus here, into a single water mass that's just Atlantic water flowing into the Arctic. That's not strictly the case. There's a lot of Arctic intermediate and deep waters here that I'm not really considering in this study. Okay, so from those data, we can get this set of initial conditions. And so I'm showing temperature salinity diagrams here, where the black dots show the mean temperature and salinity scaled by the volume transport for each of these water masses. And then in the colorful dots, these are seasonal monthly mean averages. So you can get a sense for how these vary. And on the left, I'm showing all 5 of the water masses. And then on the right, I'm showing a zoom in of just the water masses at the southern boundary. So at the southern boundary, you have 19 spiridrips of Atlantic water flowing in. There's a large circle. It's warm, salty. As part of the overturning circulation, it's transformed into something that's denser, colder, and fresher. So here's the deep water south, and there's about 14 spiridrips of that. And then you have the estuarine transformation, which it creates this colder, fresher water mass that's actually about the same density as the Atlantic water. And then the polar water north, so that inflowing cold, fresh water is a lot fresher. There's not a whole lot of it, just about a spiridrip. And then this Atlantic water north is again kind of counterintuitive because clearly the water flowing into the Arctic is not actually 16 degrees Celsius. That's coming about because there's actually a large heat transport associated with it because there's warm water going north and cold water coming south. So a large heat transport with a very small volume transport. So that's a bit of an artifact, but again, does not really affect our results here. So these are the initial conditions for the water masses. And now I'm showing the initial conditions for the surface freshwater and heat fluxes, which I get from reanalysis and this NORI-SM model. So for the surface freshwater fluxes, we have a total of 100 millispiridrips. And that's made up of a combination of sea ice melt, which is the largest slice of the pie here, 71 millispiridrips, precipitation minus evaporation. And then I think actually these numbers are swapped for the runoff from Greenland and the Nordic seas rivers. It should be, I think, 12 millispiridrips from Greenland and 5 from Nordic river runoff. And then finally, there's the heat fluxes. So you have 252 terawatts that are leaving the ocean over this full domain. And so if you put all these numbers back into this box picture, these are the initial conditions that I'll now feed into the inverse model. So 19 spiridrips of Atlantic water coming in, the transformation into these 3 different water masses, and then the other inputs of polar water north and the surface freshwater fluxes and heat fluxes. So we can put these into the model, and the bars here in this plot are the initial conditions, and they include this standard error that I use as the column weighting for the inverse model. And then the points are the inverse model solution. So the first thing you can see here is that the points don't actually look very different from the bars. And that's actually quite encouraging because it means our observations are close enough that, that they're getting a reasonable picture. So we don't have to change any of these inputs or outputs dramatically in order to close the budgets of volume, salt, and heat. The only exception is perhaps the surface freshwater fluxes, which the inverse model sort of shows us that we need more than the initial conditions. And this is a bit easier to see perhaps if I now put the inverse model solution in this sort of box framework. So indeed, we started out with 100 millisvergeps of surface water fluxes, and we need something more like 108. There's actually quite a dramatic change in the Atlantic water south. There's 19 svergeps initially, and then it decreases by half a svergep in order to get the budget to close here. And so, I mean, overall, there's a little bit too much volume, heat, and salt that's flowing into the domain. And so when we run it through the inverse model, some of the big adjustments that are made are to this Atlantic water south again, and the surface water, the surface fresh water, just to make sure everything balances. Again, as close as possible to the initial conditions from the observations. Okay, so now that we have a closed budget, we can actually get at trying to answer this question of how are these different freshwaters, so the polar water north that's flowing in through Fram Strait, and the surface freshwater fluxes, sea ice melt, precipitation, land ice melt, river runoff, how are those different types of freshwater split between each circulation component? So we have the three circulation components that are defined by their outputs. So the estuarine, sort of defined by this polar water south output, the overturning, it's defined by this deep water south output, and then the Atlantic water through flow, which is defined by this Atlantic water north output. And in order to solve this, we'll make the sensible assumption that none of the polar water that's flowing through Fram Strait is mixing into this Atlantic water through flow limb. So we'll assume that's sort of a separate piece of the circulation, and this Atlantic water isn't mixing with polar water that's flowing on the completely other side of this box. So we can solve the volume and salt budget for the Atlantic water through flow limb, making that assumption. And we find, using these salinities and temperatures, that we need 9 millisvergeps of fresh water to evaporate actually from this limb in order to get the final product of the Atlantic water north. And that leaves 117 millisvergeps of the surface freshwater fluxes now for the overturning and estuarine circulations. Okay, so now we can do a little bit of a thought experiment just to kind of explore the parameter space of the solutions for these two limbs that we're really interested in. So first we can say, what happens if none of the polar water north participates in the overturning circulation? What if all 1.2 svergeps of the polar water north is part of this estuarine circulation? How much surface freshwater would have to participate here in order to close the volume and salinity budget for this limb and this limb? And then we can place that in a parameter space. Okay, so I'm showing now in panel A, the estuarine limb, in panel B, the overturning limb. And on the x-axis, I'm showing how much polar water north transport is participating in this particular limb. And on the y-axis, I'm showing how much of the surface freshwater is participating in this particular limb. So, in this extreme case where I've said, none of this polar water participates in the overturning limb, the solution is here at 0 for polar water north transport. And then in order to close that budget, we need 92 millisvergeps of surface freshwater flux. And similarly here, if we say, okay, all 1.2 svergeps of the polar water participates in this estuarine limb, then how much, then we need 24 millisieverts of surface freshwater flux to close, again, the volume and salinity budgets. And then we can do the thought experiment at the opposite extreme. What if no polar water participates in this estuarine limb? Then our solution is somewhere here. We have zero polar water north here. So we need a lot more surface freshwater flux in order to close these budgets. And sort of same idea again here. Okay, but we know, probably neither of these solutions are the right one. And in fact, polar water likely flows into both circulations. And our real solution is going to be somewhere along this line. And we can get a first sort of guess at where on this line we're likely to fall by looking at how the surface freshwater is geographically distributed and how much likely participates in each limb. So here are the 3 different sources. So precipitation minus evaporation, runoff, which includes Greenland runoff as well as river runoff, sea ice melt and freeze, and iceberg melt is actually, I think, in this sea ice melt and freeze as well. Okay, so then I can, the black lines show the southern and northern boundaries, as well as the boundary between roughly the sort of east and west. The estuarine circulation kind of flows along the coast here. And we find that taking these all together, about 47% of the surface freshwater fluxes flow along in this sort of western part. And the remaining 50% are in this overturning circulation and Atlantic water through flow part. So we can use this now to constrain the parameter space.
Can I interrupt you one moment?
Yes, please.
So there's a question in the chat from Allegra. She's asking, can't we use water isotopes to help to distinguish the provenance?
Yes, definitely. That's another way that this sort of thing could be done. But I haven't done it here.
She says, okay, thank you.
Okay, so we can estimate here that 47% of the surface freshwater participates in the estuarine circulation. Draw this dotted line from surface freshwater flux, 51 millisieverts, and we get about 0.6 spherotrops of the polar water north that participates in this estuarine limb, and do the same sort of thing for the overturning circulation as well. And so this now gives us an answer to this question: how much Arctic freshwater participates in the subpolar overturning circulation? We now have numbers on each of these arrows. And the basic answer is that about half. So about half of the polar waters that are flowing through Fram Strait participate in the overturning circulation, plus a really substantial amount of surface freshwater fluxes that enter over the Nordic seas and eastern subpolar gyre. And this is consistent with transport offshore the shelf break, as well as generally with the literature. So I appreciate Allegra's question. It would be interesting to see to what extent this is consistent with isotopes. I think there's a study by Dodd et al. That shows using isotopes. I could be wrong, because this is not really my area, but I think they show that there's a substantial flux of sea ice into the Nordic seas using isotopes. But what I am sure that it's consistent with is these transports. So we have the transports through Fram Strait from this Distur and Tsubuchi products that are going into this model. And from that, if you take the transport onshore of the 500-meter isobath and offshore of the 500-meter isobath, that's about a 50-50 split. So, and this is consistent with the idea that about that all of the waters that are offshore of that 500-meter isobath mix into the interior and can affect convection and sort of mix into the overturning circulation. And then Focal et al. Also showed using some ice mass balance drifters that everything that's on the shelf flows right along the shelf all the way along the coast of Greenland, whereas things that are, the water or sea ice that starts off further offshore is much more likely to be mixed in. So that's encouraging that this sort of budget from observations agrees well with other estimates from the literature. Okay, and then as sort of a final note here, I've made a lot of assumptions to get to this sort of coarse mean budget from the observations. So I ran a few sensitivity analyses, some of which I'm showing here, to try and understand how sensitive my results were to the different assumptions that I made. So one of the big assumptions I made is that the water mass, salinities, and temperatures are constant over time. So the Atlantic water was given one salinity and one temperature. The polar water is given one salinity and one temperature, and then all that I allowed the model to vary is its transport. So in this yellow line, I'm showing the solution in the case where I allowed the polar waters to be fresher by 0.5. And the reason I did this test in particular is that the polar waters are probably the least well observed of all the water masses. The moorings that we use can't reach the surface because they'd be knocked over by icebergs. So we have to sort of extrapolate and estimate, what the salinity of the coldest, freshest waters up at the surface are. It's likely that we're overestimating their salinities. So that's the yellow line. And then the green line is what if we added 20 millisieverts of surface freshwater? So, I did a comparison of different reanalysis products, and some of the other reanalysis products showed more precipitation, for example, and often large ranges. So, I tested what if you added 20% more surface freshwater flux, how would the results change? And you can see that the specific numbers change quite a bit. So, I wouldn't bet on the specific numbers that I showed you. But what is consistent from test to test is that there's a substantial amount of polar water, so on the order of 0.5 spheredrops, that is mixing into the overturning circulation. The overturning part is a lot better constrained. And in general, you get the sense that there's a pretty even split between the polar water participation here in the estuarine limb and in the overturning limb. So that general result is robust to these pretty significant uncertainty tests that I've done here. Okay, so just to reiterate my main conclusions, I've asked this question: how much Arctic freshwater participates in the subpolar overturning circulation? And the answer again is about half of the polar waters that are flowing through Fram Strait, and then substantial surface freshwater fluxes as well. And one of the sort of consequences of this is that an Arctic freshwater release might be more likely to impact the overturning circulation, at least on shorter time scales, than Greenland melt. Just because it's entering the system closer to where deep waters are formed, and we can see that in the present day breakdown, already a significant amount of those fresh Arctic waters are participating in the overturning limb. And I think this framework could be applied to compare models with observations pretty effectively, and try to understand if the models are in the same kind of parameter space that the observations are in. Before completely turning over to questions here, I also wanted to just highlight some of the other ongoing work that I'm doing. So please feel free to reach out to me about these other projects as well. So I'm working on the Beaufort Gyre observing system. This is the Arctic's freshwater reservoir And I'm particularly interested in how this gyre, which has been accumulating fresh water over the last 20 years, how that interacts with the North Atlantic. So how might the North Atlantic be affected if some of that fresh water were to be released? I'm also continuing to work in the subpolar North Atlantic, looking at boundary current dynamics and their connection with overturning. And I'm also starting to get interested in ventilation. So I deployed some oxygen sensors on the OSNAP moorings last summer. And I'm interested in how oxygen enters the water column, both through convection and also within boundary currents. And then finally, I'm working with Josh Willis to build an AMOC data set in the subtropical North Atlantic. So combining moored observations, shipboard observations, as well as satellite altimetry, GRACE, and Argo floats, trying to put those all together to get an AMOC data set that is between RAPID, which is down here at 26 North, and then OSNAP, which I talked about today. So with that, I will thank you for your attention and take any questions.
Thank you very much. Have canned clapping or something. That would be neat. Does anyone have any questions from the group? I see there's a question in the chat from Laurie. I hope you don't mind. I might pick on you because I think it'd be nice to have different people.
Yeah, that's okay.
Thank you.
So the question was, is the assumption that freshwater input with T equals 0, is that a good one? I'm thinking of warm rain or the latent heat associated with snowfall or the sea ice melt in the icebergs, or is that all taken up by JRA 55 analyses?
Yeah, that's a great question. And actually, one, I haven't considered that specifically, but what I have done is kind of related is I've run this using sea ice as a solid component. So I've separated out sea ice and accounted for the latent heat that it requires to melt sea ice. So given sea ice a temperature, and that it didn't change the overall results much, which is what I was looking for. So I imagine that changing those would be a small difference, particularly because their volume fluxes are so much smaller than the oceanic ones. So they just wouldn't have as much weight in the overall budget. But that's a good question. I can certainly look into that.
But the latent heat associated with melting is large, right? So the effective temperature of the solid ice is minus 90 or some strange number like that.
Yeah. So I think I did it with minus 30 just to allow for some melting by the atmosphere as well, since the budget doesn't include the atmosphere, but just the ocean. But even though those temperatures are so large, because the volume is so small, I think that's why it doesn't impact the results overall.
Okay, thanks.
So I also see in the chat we have a question from Olga. Olga, is there any chance you would like to?
I'll try, but my connection isn't great, so I might start breaking. That's why I typed it in. So yeah, how much does the contribution from Greenland have to increase? Or could you give a rough number? What the threshold, if you wish, for it to start to matter?
I guess, so I can show, right now the Greenland runoff, at least coming into the east of Greenland, is something like let's see, 20-ish millisphere drips. And then the total surface freshwater flux coming into the whole region is 100 millisphere drips. So there's a lot of sea ice melt that's making up most of that difference. And yeah, I guess in order for it to have the same impact as sea ice melt, it would have to grow by a couple times its size. I think, you know, one thing I will say though is that this framework is really, it's just trying to count things. So I don't have any dynamics in here, and I'm not really, you know, acknowledging how these different things might enter the system differently or affect the dynamics or circulation differently. So I guess I wouldn't want to say that the Greenland part doesn't matter or that it's not.
No, I realize, but still, yeah, it's not a reason for the question. I suppose I could formulate the question and ask how much the freshwater input has to increase to change, say, your split between two limbs, that sort of thing.
Yeah. Yeah, that's a good question. I mean, I guess I can go back to this uncertainty parameterization, these uncertainty tests I did, and you know, even including 20 more millisphere drips of surface freshwater flux, for example, didn't change this partitioning much. On the other hand, you know, if the circulation changes enough such that this partitioning doesn't really make sense to do, then that's kind of irrelevant. But yeah, overall, I do think it would have to change by a couple times to really change this picture a lot.
All right, thank you. Yeah, thanks.
Yeah, that's really interesting. It makes me think of what future scenario might exist where the melt from Greenland is larger, but the melt of sea ice perhaps is less diminished. Is there a scenario where that's the case? But are there
and then there's also,
sorry.
Oh, I was just going to say, you know, the Greenland melt also can enter deeper in the water column, and there's some evidence that it can persist longer deeper in the water column. So it might affect the circulation in a different way than you know, forcing that's coming from the surface. And that's not accounted for here.
I'll ask another question then, Craig. So you partitioned the freshwater flux out of the Arctic into solid and liquid, right? You had about the same amount coming out through the northern into your domain in each form.
Mm-hmm.
If you change that, if you change from sea ice to liquid coming out of the Arctic, does your model framework allow for investigating that balance? Or
yeah, so what I did is actually a little bit different than that. I don't have the sea ice flowing into the domain. I just account for it where it melts. So it sort of, you know, in the basic picture I presented today, it enters the domain when it becomes liquid. And then I did a separate test where I allow it to be solid and you know, account for its melting as well. Does that make sense?
so the budgets are only on the liquid freshwater.
Mm-hmm. Yes. Exactly.
So if the sea ice all came out of the Arctic and just went all the way to the south of your domain, it wouldn't show up at all.
Yeah.
But if there's more melt within the Arctic, presumably the total amount of fresh water that's coming out of the Arctic has to be about the same, whether it's a sea ice or fresh water.
Well, I guess that would show up in my budget as a lower salinity of the polar water that's coming in.
Yeah,
if it were to
okay,
melt further north.
right.
Mhm. Yeah. And the sea ice, it does all melt in this domain before it leaves, pretty much. Very little sea ice.
Yep.
South
Okay.
of Oceanic East.
Do we have any final questions?